Today we'll start with an introduction of analog mixed mode VLSI. This is a professional elective with the subject code as 18EC742. I've given already what is the importance of it, what are its the job opportunities, what will be the salary criteria. These few introduction part I already given. So I'll be starting with the not exactly the syllabus, but I'll introduce you to the course. So here the total syllabus is containing of 5 units. For this we refer to the textbook with the author Jacob Baker. The link of the book is given here, and even I have shared the textbook over the Google Classroom, so you can refer to that. And from with respect to that textbook, the 5 units which are taken and the scores are, so the first unit is amplifiers. It is taken from the chapter 22 of Jacob Baker textbook, that is analog mixed mode VLSI design. Second chapter is differential amplifiers. It is from the chapter 24 of author Jacob Baker. Third chapter is operational amplifiers from chapter 25. Data converters fundamentals from chapter 28 and data converter architectures from chapter 29. The complete plan of this course, already you know these things, but still only I would like to stress upon the part of compensatory IA. Here, third, fourth, and the fifth units will be the portion for compensatory IA. OBA1 and OBA2 are given from 1, 2, 3, 4 chapters, and the course activity will be given from 3, 4, 5, and quiz will be taken from 4 and 5. To start with, before I start exactly the amplifiers unit, that is the unit 1, some of the keywords that we use, we'll get familiar with those. First one we take up it is MOSFETs. So the MOSFET is nothing but a 3-terminal device. It is a voltage controlled device. That's why the name field effect transistor. Here we define a word called long channel MOSFETs and short channel MOSFETs. Long channel. So this is spoken with respect to the length of the channel. All of us know the channel is nothing but the separation between source and drain terminals. The long channel MOSFETs are the MOSFET concepts that we referred or the studied in the CMOS VLSI design. The short channel MOSFETs will have the channel length to be lesser than 1 micrometers. So it comes in terms of the nanometers. So those are called short channel MOSFETs. Then the short channel MOSFETs and effects are slightly different. So here the drain induced barrier lowering, velocity saturation, quantum refinement, confinement, and hot carrier degradation. These are the few concepts that arise in the short channel MOSFETs. Continue with that. Next is the small signal analysis. Small signal analysis. This is used when we want to analyze the AC circuits. So because the amplifiers will be used to amplify the AC input signal. To analyze these AC circuits, we refer to the small signal analysis. The small signal analysis includes the small signal model of the MOSFETs. The concept goes like this. So these amplifiers initially has to be biased to a particular operating point where we get a maximum amplification. So this biasing point defines the drain current and the VDS voltage at the particular VGS voltage. So these are the 3 parameters are defined by the operating point. The MOSFET has to be biased such a way that it is operating at those biasing points. Once we make the MOSFET to operate at those using the biasing circuit at that particular operating point, then it acts as an amplifier. Once it is biased at a particular operating point, then AC signal is applied. So what is this small signal model of the MOSFET? So you can observe in this figure the small signal model of the MOSFET. You can see here the common source amplifier circuit is shown. If you observe the first figure, at the input of the gate terminal, source Vs, AC source is given, then a DC source is applied. At the drain terminal, RL resistor, then we have VDD in series with it. Here, this VDD and DC source connected at gate, they are biasing voltages. Then signal which has to be amplified is an AC signal, that is nothing but Vs. So while the small signal analysis considers the MOSFET small signal model, you can observe here. First of all, see that gate and source are unconnected. In between those, plus and minus VGS voltage is shown. What it means? It means from the gate to the source there is no path defined, means no current flows. There is only a voltage VGS in effect. Then at the source terminal, at the drain side if you see, we have a controlled source, a dependent source. The dependent source is a current source. It depends on what? GM and VGS. VGS is the input voltage. That is, you have seen between gate and source we have only VGS, no? So that current source depends on that VGS and GM is the transconductance. So what we see is between drain and source we have voltage controlled current source. In parallel with that, R0 resistance is present. It is the output resistance. So this is the small signal model of the MOSFET. Then the GM stands for the transconductance parameter. This transconductance parameter is the slope that we obtain from the input characteristic graph, ID versus VGS. Here GM is defined to be the ratio of ID versus VGS. ID defined by ID divided by VGS. ID is output current, VGS is input voltage. In general, current divided by voltage is a conductance. But since here output current divided by input voltage, so we add the word trans. Therefore only transconductance. This is an important parameter because it defines the gain of the device. Because see, the output is the drain current, input is the VGS voltage. The ratio of the two gives you the gain factor, output divided by input. So it is gain factor as well as, so GM is the gain factor, and these are the some of the keywords. Here you can see that the quiz is given. Try to attend this quiz. Thank you everyone.